Okay, so last time we began our adventures in chapter 11, looking at explanations, and more specifically in causation. And we saw the two types of explanations: the physical, in which the explanation is presented in terms of the hard sciences, so-called because the classes are often hard to pass, things like physics, biology, chemistry, neurology, etc. And we also looked at the behavioral explanations, which deal with the thinking and feeling stuff, divided up by the soft sciences, like psychology, anthropology, etc. And the main difference is with the physical stuff, it's purely mechanical, physical explanations, whereas with the behavioral, it references the psychological in terms of the feels and the things. Now, of course, as we saw, there's some interesting metaphysical debates about, is the mental purely physical? Is there really a difference, etc., etc.? But as a sort of common sense distinction, we'll distinguish, say, between the working of a machine, like a thermometer, and people's thinking and feeling. And then we turn to looking at sorting out individual causation. And this is the stuff we typically do in everyday life. We want to know, for example, if you have a phone and you get up in the morning, before you go to sleep, it's Apple's updating the iOS. Then you get the next day and you just turn it on and can't get past the lock screen. And of course you wonder, why can't my phone? And so you'd have to be faced with a causal problem. Or if you do really well in an exam, and suppose you're kind of surprised by you go in, you're like, oh, this is going to be terrible. You get like an A+++. You're like, wow, how'd that happen? And you want to know why, so you can make that happen again. And what these scenarios involve is trying to explain causation on the individual level. And so to do this, what we do is this. First, something happens. Often something bad. Your phone won't phone anymore, or you feel tired, or the test didn't go well, or someone at work suddenly starts acting really mean and obnoxious towards you, or maybe something good. Your phone works even better. People at work are super nice and you get a promotion and a raise. You do great in all your stuff. And so you get a situation which either you want to put an end to, like something bad, or keep going, something good. And so to do this, what you do is form a hypothesis. Here is perhaps why this is happening. Now, how do we sort out what causes what? Well, as I mentioned back in the ancient days of Thursday, we go back to our good dead friend, John Stuart Mill. English guy, around the 1800s, died in France, not because he was in France, but because he was old and stuff. And he's best known for probably utilitarianism, the theory of the greatest good for the greatest number, or the ends justify the means. Now, he developed three methods: difference, concomitant variation, and agreement. And they're given various and sundry names, so they go back to our good dead friend, John Stuart Mill. So here's how the method of difference works. As the name implies, to make this do its thing, you got to have a difference. And it's kind of like the, to use an analogy, it's kind of like the old Sesame Street stuff, which was around when I was a kid, it's been around forever. And they would have this, I remember they had like a bit where it's like one of these things doesn't belong. And you're looking at the difference. So how does this work in terms of its mechanics? Well, here's where you can apply it. You need a scenario where you have the effect you're concerned about, be it something good, like suddenly you're doing great on a test, or everyone's nice at work, or suddenly you get a promotion out of the blue, or something bad, the phone doesn't work, people are mean, etc. And then you need at least one scenario where the effect didn't occur. Now, this could be happening at the same time. For example, suppose you're running a small business and you have a couple servers, and the same server, etc. And one of them is going fine, the other one is just repeatedly crashing. So half your servers are down for your startup. Or it could be the same thing in different times, like your phone. Phone was working fine before, and now the phone won't phone. So you're trying to figure out the difference. So the minimal requirements for this method are: an effect occurs in at least one case, and doesn't occur in at least one other case. And again, this can be the same thing over time, like a change in a thing, or it could be a scenario where you have two different sets of things that are related. And what you're trying to do, as the name implies, is find out what is the difference that made the difference. And sort of in the ideal, pure sense, here's what you do. You look at the two cases, and ideally, in terms of the method, you'd want multiple of each to look at. Because if you just have two, then it becomes, it's less accurate. And ideally, you'd want multiples to look at. Now, if it's something bad, of course, you don't want lots of bad stuff to happen just so you can figure out why. But in terms of getting to the bottom of it, the more of each case you've got, the better chance you have of sorting things out. So you look at the two scenarios, and what you try to find is, what is the difference between them? Now again, in the ideal, sort of the perfect scenario, the two would be utterly identical except for one thing. And the one thing that's different, that would be your cause. For example, going back to the server example, if one server is working, one's not, and the only difference between the two is this one, you just added some new memory to, well, in that case, if that's the only difference, that's almost certainly the cause. In other cases, it'll be maybe more complicated. For example, suppose you're a doctor and your specialty is investigating outbreaks of foodborne illnesses. And you have people who are sick, people who are not sick, and based on the symptoms, you say, aha, food poisoning. But of course, people eat a lot of stuff. So you have to figure out, what are the people who got sick, what did they eat, or what did they get exposed to, that the people who aren't sick didn't get exposed to. And as you might imagine, given how much different things people eat, you can have all kinds of things you have to sort through. And also making the matter more complicated is that the actual cause might sometimes be present when the effect is not. Like in the case of food poisoning, the person's response to it depends a lot on their immune system, how much they consumed, etc. So one person may eat contaminated stuff and be completely fine. Someone else may be exposed to just a little of it and be in terrible, terrible shape. And so it can get really complicated. But in the ideal, the method works like this. So here's the paradigm. Minimum requirement, two cases. One where the effect occurs, one where it does not. What you look at to use a method, you look at what is the difference between the two cases, and in the ideal, the difference between the two will be the cause. Where are complications? Well, some complications can occur where, as I mentioned, like in the case of food poisoning, you might find the cause present where the effect is not, because the cause might not be like 100% guaranteed to produce the effect. So some people are very resistant to food poisoning. They can eat all kinds of horrible stuff and not be affected. Other people are much more vulnerable. You also, of course, may find other differences that make no difference. For example, you might find, by pure chance, everyone who didn't get sick, maybe they, by pure chance, they also smoke, or they consumed alcohol. In that case, you may think, well, maybe that was a factor, maybe smoking or drinking did something, but it may turn out just to be pure coincidence. And so it can get complicated because, again, you may have the cause present where the effect is not, because resistance and probability, and you may have differences, quite often you'll have differences that don't amount to anything. So sorting through stuff can be challenging. So the way you use method is pretty straightforward. It's a very effective troubleshooting or keeping the good thing going method. Again, you've got a scenario where something's changed, or things are different, effect, not effect, and you wonder why. And the thing to do is look at the difference. To give another practical example, today we're all super reliant on technology. Can't function with our phones, tablets, laptops, etc. And of course, even though they're vastly improved compared to going back to like the 90s, the 80s, they still can have problems. And so when we're troubleshooting the problems, this method is very useful. So if something goes wrong with your computer, or you're taking like a test on a blackboard and something goes wrong, the thing to do is look at what is the difference? What has changed? Did I do something differently? Was there a software update? Did I install new software? Did I add a new driver? What happened? And it's a very effective method for discerning troubles like that. Also good in life in general. For example, say you normally feel pretty good and energetic, and you start feeling like down, lethargic, and slow. A good question would be, what has changed? What would bring about that effect? Is it that you're not getting enough sleep? Maybe that's a factor. Did your diet change? Maybe that's a factor. Is there more stress in life and work? Maybe that's a factor. And so you look at things that change. So if it's something bad, you want to say, what's making this bad? How do I stop it? If it's something good, you'd say, what's making it good so I can keep the good times going. Before going to agreement, anything about difference that needs more stuff. So in terms of putting this in your critical thinking, causal reasoning toolkit, when you want to figure out what caused something and there's been a change, a good question is to ask, what is the change? What was the difference? It's a really useful, but fortunately very simple method. Now agreement, as sometimes known as common thread, the name kind of gives it away. It's agreement. So in the case of agreement, what you've got is this. Like difference, and this may seem odd, but it will make sense in a second hopefully, you still need two cases, at least two. And in the case of agreement, the effect is present in both cases. And like with difference, the more you have of cases in terms of doing the reasoning, generally the better. Now again, if it's something bad happening, you don't want lots of that bad stuff, but from the standpoint of sorting out what's going on, the more the better. And what you do is you look to see what is the common thread. What do the two have in agreement or common? And so in an idealized sort of perfect scenario, you have the effect present in both cases, or sets of cases. You'd look at all the factors, and you'd see what, instead of the difference, you look at what do they share in common. And again, in the ideal paradigm case, that would be the cause of the effect. For example, we can go back to the scenario, suppose you're a doctor investigating foodborne illnesses for the state of Florida, or whatever state you like, just making it up. And there's cases of people showing, E. coli, sickness. And you go and see what do they all have in common. And you find that in the ideal, they've eaten and consumed all kinds of different things, but then you find one they all have in common is they all have this spinach, this bagged spinach. And no one, everyone in that group ate the bagged spinach, everyone who's sick. And so that would be the common thread. Everything else is different except for that spinach. So what you would infer is, the common thread among all these cases is the spinach. Therefore, the spinach is probably the cause. Now you can also use this in individual cases where things are just staying the same. So for example, if you feel tired and you keep feeling tired, you keep feeling tired, and low energy, as Trump would said, you want to see what is it that's going on that's constant in all these cases. So suppose like your sleep is varied, your diet is varied, but then you find, you're in a stressful situation, so constant under stress. In that case, you'd probably think the stress is probably a causal factor. Now there's also a version of this, as I mentioned, there were three originally, difference, agreement, and concomitant variation, and the authors took concomitant variation and stuck it into agreement. Now, here's how that works. What we're looking for is, in the case of agreement, is correlation. That there's a correlation between the suspected cause and the effect in every case. But of course, it's a super popular saying, but a common saying that correlation is not a causation. Which is true. Just because things hang out together doesn't mean one causes the other. And so we're trying to sort out what things are merely correlated from what is the cause. Now there's also what's called covariation. And covariation works like this. It is, of course, so going together, like co-op, and variation, meaning varying, so they vary together. So we can use a badly drawn bar graph, or rather a line chart, sorry, to demonstrate this. So if two factors are correlating, one way is positive correlation. As one increases, the other also increases. So they correlate, increase, or as one decreases, the other decreases. So they vary together. And of course, there's also, kind of the inverse of that, whereas one increases, the other decreases. Common examples would be one increasing, the other increasing, would be generally like training and athletic performance. They generally go up together. So you hit at a certain point, you start overtraining, and then it goes back. Also, like studying and performance in class usually tend to correlate positively. Exercise and aerobic exercise and weight tend to have a negative correlation. The more aerobic exercise you do, generally you start losing some weight because you're burning off calories. And as I imagine, there's all kinds of things that correlate. Now, the challenges in the case of correlation is sorting out when the things actually have a causal connection and when they just correlate. And again, we have that saying, correlation is not causation. Now, the method of agreement is a way of trying to sort that out. We're trying to sort out, in the case of things that are correlating, trying to sort out, do they actually cause each other? So we find, in every case of the E. coli contamination, we find the spinach. So we'd say, well, probably a cause. Or in the case of covariation, if we find that in cases where people get less and less sleep, their memory gets worse and worse, we might suspect that there's a causal connection there. And we look to see, is that real? Or is it just correlation? Now, the mistakes of taking correlation or covariation to be a cause are so common, they get their own fancy Latin fallacies. And they're pretty old fallacies. First one, more recent, is cum hoc ergo propter hoc. Translated to English, with that, therefore because of that. And as we'll see in more detail in the future, this is a fallacy that occurs where someone says, aha, two things are, they're co-varying with each other, or this way, therefore there is a connection. And they do it too quickly. They don't go through the proper process. So this fallacy occurs not because the person is automatically wrong, they could turn out to be completely right. For example, let's take the correlation of lifespan and time spent in pro wrestling. So there's a correlation. People have, the more time people spend in pro wrestling as pro wrestlers, their lifespan tends to decrease. So, or another correlation would be the more time people get concussions in football, the more likely they have to have brain injury later on. And those would be correlations. But the question would be, is there really this causal connection? So you have to sort that out. So the challenge here is sorting out when correlation is causation. And if we get it wrong, I mean, it could be completely wrong. We could say, aha, look, the more concussions a person has, the more likely they are to have brain injury, definite cause. And that'd be too quick. Even though it's totally true, the problem is not that the conclusion is not true, the problem is the reasoning is too hasty. It's leaving too quickly. Secondly, the classic, probably the oldest, the most famous causal fallacy, the post hoc ergo propter hoc, and it's been around so long, it usually just gets known by its first name, post hoc. Translation, after this, therefore because of this. And as we'll see in more detail in a bit, it occurs when someone says, well, this happens, so this is going to be the cause of that. And again, the person could be completely right. So, for example, if someone finds out, aha, everyone knew who's got food poisoning, ate spinach, spinach is definitely the cause. They could turn out to be completely right, but they reason too quickly. The problem with these fallacies, again, is not that they get the conclusion wrong. In fact, it's a fallacy to conclude that a fallacy gives you a false conclusion, is that the methodology is, in error. So a fallacy could totally lead you to the truth by pure luck. So the problem is not being wrong, the problem is bad logic. Before pressing on to our next exciting slide, anything about this? Or pro wrestling that needs more stuff? So in sorting this stuff out, as they used to say on the after-school specials, knowing is, half the battle. Because the more you know about how stuff works, the better you are at sorting stuff out. Which is why, one thing that people, older folks, promote about is how today people can just look everything up on Google. They don't need to remember stuff anymore. And of course, this is the same complaint made, presumably when they invented writing. People are probably saying, oh, these kids with their fancy writing, they won't have to remember everything, they can just write stuff down, their brains are going to melt. Everything is supposed to melt people's brains, and it all did, so there we go. But one reason why it's still worthwhile, because you may wonder, like, why do I have to learn stuff when I can just, go on the Google, and the Google knows all the things? Well, a reasonable, reason for this is before you can even start working the Google, you've got to know stuff. You got to know where to look, etc. And there may be cases, those rare cases where you cannot get to the Google. So background knowledge is still very useful, because what you do essentially is you encounter a scenario, and you've got to figure out what's cause and what. And the more you know, the better you'll be able to process it, the better your understanding. I mean, an easy and obvious example is most people know someone who's like really good with computers. And whenever you have a problem, you go and get that. And back in the 90s, computers were, it's kind of the early days of computing, and there were all kinds of problems. So it was always that, person's relative or friend who just spent constant time doing all this stuff. In fact, one of the reasons why I got tenure, because I was the person who kept all the computers going in this building back in the ancient days, because I understood IRQs and so forth, which are interrupt requests. Fortunately, I never have to deal with those. Those were terrible. They can make it so if you put in a video card, your mouse would stop working. Good times indeed. So, knowing stuff, like about computers or, nutrition, etc., again, it's still useful. And the more you know about stuff, the better you are at handling things. Which is, in a way, kind of obvious and not surprising, because someone who knows medicine, they're better at, medicine stuff. Someone who knows engineering, better at engineering stuff. And this also kind of explains why it's still good to know stuff, even when you can just look stuff up. Because to know what to look up, and to know whether it's legitimate or sketchy or not, you still got to know the stuff. So what we do with these methods essentially is this. Typically what sets it off, but not always, again, is something has occurred. And what we'd often do is have the effect present in multiple cases. We can use the example of, let's say you go to medical school, you start working for, a state agency that deals with, food, borne illness, etc. And your job is investigating, you have your own, I guess, maybe your show, you're like doc investigator or something. I guess the MSI, Medical Scene Investigator, Tallahassee. Part of the CSI series, I suppose, when they run out of CSIs. So you have this outbreak of foodborne illness, you have all these people who are sick, and then you go through and look at what do they all have in common. You find, aha, the bag, spinach. Then the next step would be this so-called best diagnosis method. And what you do is you'd say, well, okay, in all these cases I have found the spinach is present. Now at this point we're using the method of agree. We'd say, yeah, it's probably the spinach. But if we're going to confirm the hypothesis, there's sort of two parts to figuring out stuffs in the science methods. And they go back to philosophy of science, which is philosophers trying to tell scientists how to do their business, which they love, because everyone loves people telling them how to do their job. Now, way back in the 1920s, there were some philosophers who decided that what you had to do was verify stuff. If you want to make a claim that was meaningful, you had to be able to prove that it's true. So part of the sciencey stuff now is proving stuff is true. I mean, that's what part of how science works. You try to show, okay, the spinach is the cause. We're going to try to prove that. Now, one thing that arose, and it's why, if you ever heard philosophers often talk about the black swan, not the movie, but the black swan issue, you may wonder, like, why do they talk about that? Well, there's one. It used to be a standard example in European logic classes that all swans are white. Because as far as what Europeans believe, that was true. And then Europeans went to Australia and saw black swans. And they were like, they're swans, but they're not white. So it used to be an established fact that every swan that was seen was white. All swans are white, until you encounter the black swan. And so it pointed out, with a particular example, a general problem. You can never know for sure that, like, all swans are white or all one thing or another until you see all those things. And you can never really know that you've seen all those things. And so they have this sort of solution where instead of going with verification, you've got to like examine everything and prove it to be true. You go with falsification, which is you try to show that it is false. And so until you show it's false, then it's considered true. Because if you have to try to prove it to be true, like all of them, you're not going to do it. Because you have to encounter, like, suppose we say all swans are white or black. And it's true, all the ones we found on the planet are white or black. But imagine there's a planet of purple swans. Spoiler alert, they're going to come and kill us after the robots don't get us. In that case, we have to say, well, then we were wrong. And they would falsify our claim. So what we do now is we try to like prove stuff, verify it. We also try to falsify it, try to show that it's not true. So the sciencey stuff is trying to do experiments that try to show we're wrong. And if they don't show we're wrong, then we say we're probably right. And so when we test our hypothesis, we first would go, well, okay, we got spinach in all these cases, we got our correlation, probably a cause. Then we test in the following way. If spinach really is the cause, we'd expect there to be people who are sick ate the spinach, and people who are not sick didn't eat the spinach. And then we'd apply the method of difference. So we look at cases of people that are similar, we try to match them up that are similar, and see that aren't sick. So we'd find people who aren't sick in this case, apply the method of difference, and if we find that none of them, or most of them, because people get different resistances, didn't have the spinach, then we'd say that our hypothesis has probably been confirmed. Now, if we find that lots and lots of people ate the spinach too who didn't get sick, then we might consider that to be falsifying our hypothesis. Because if the spinach is the cause, we'd expect it not just to be present in all cases where people are sick, but also generally not to be present in people who aren't sick. Now, of course, here's a complication. Unless the causation is like 100%, you will find cases where it's present and the effect is absent. And food poisoning is a common case like that. There are lots of people, probably all of us, have eaten contaminated food, like lots of times. I've done the thing where I go into Publix, it's like, oh, that was recalled. Oh, good thing I ate all that yesterday. I'm sure I'll be fine. And I was fine. Even though it was totally contaminated. So we don't always get sick. And so the method basically involves applying those two. So typically we have something occur, like foodborne illness or something, catches our attention, we run method of agreement, and then we run method of difference to see if it actually holds in trying to confirm the hypothesis. And if it goes through both, it's present in all the cases of the effect, and ideally it's absent in all cases where the effect doesn't occur, then we'd be pretty confident it's the cause. Now again, we may have some complications. We may have like cases where someone got sick from something else, so the spinach is not present, and we may have cases where someone ate the spinach but didn't get sick. But those would be complications we'd have to take into account. But in the ideal form, it would be 100% and then 0%. And then we'd say, we're probably right. And this is the best diagnosis method because you'd say, well, this best explains it. So if we find the spinach is present or highly correlated to cases of illness and absent or highly, generally not present cases where people are fine, we'd say the spinach is probably the cause. Now this method is inductive, so you can always be wrong. It could turn out, you could go through all this stuff and say, yeah, most likely the spinach, and then it could turn out to be something else entirely, which sometimes does happen. Now, this induction thing is something we always have to watch for. There's always a jump, so we should always consider we could be wrong. And one thing when people don't take into account for it, they'll often take a unjustified critical view of science or reason, like, oh, they got it wrong, they're always wrong. Well, yeah. In fact, you expect things to go wrong because it's inductive method. It's just probability. It's always a chance, no matter how careful you are, things could go wrong. But not using it, you're way more likely to get things wrong because then you're just guessing stuff. Now, another kind of weak point there is because you can always say things can go wrong, and there's always a way to sort of, explain, differences. Like, for example, when I said we may have cases where people do get exposed to the spinach and don't get sick, the spinach can still be the cause, then someone could raise the doubts, well, how do you know that the spinach is the cause? Because, look, it's present here and they're not sick, so I'm raising doubt. So, for example, think of the flat earth view today. Super popular, apparently. And they run, experiments. And some do run experiments, like there's the gyroscope experiment, the light experiment, the observation experiments, and they'll get results that seem to show the Earth is not flat. But what they can do is, of course, say, well, there's some factor maybe that, corrects for it. Like in this case, you might say, maybe it's not the spinach that's contaminated, maybe it was something that was with the spinach, the dressing or something. Or in the case of like a particular test, someone may bring in some other factor and say, well, yeah, we got the result we expect from a flat Earth, but there's some other factor confounding it, so we still can't be sure. And one thing that allows conspiracy theories, kind of room, is induction, because you can always legitimately say, yes, no matter how well you test it, you can still be wrong. And then it also holds the opposite way. No matter what you try to disprove something, like trying to show the Earth is not flat, you can still be wrong. And hence, people can use these methods and still end up, rejecting something like the Earth being round. And not being irrational, it's applying these methods, kind of. Okay, so these are both pretty useful for getting through life. And again, we use them all the time. Things go wrong, something changed, it goes wrong, we wonder what happened. We look at the difference. Something, happens in all cases, we say, what do they have in common? So, from a practical standpoint, for tests, quizzes, etc., how do you sort them out? Well, typical questions would be like true, false about their definitions. Also like example questions. And here's how to tell. With agreement, the giveaway is there'll be the effect present in every case and the suspected cause. That's the giveaway. So, for example, the question is true or false. This is an example of method of agreement. Dr. Jones found that every case of food poisoning involves someone eating spinach. She concluded that spinach was the cause. And that, of course, would be true. It's fact present in every case, cause present in every case. With method of difference, way to spot that is, well, difference. In this example, question like true or false, Dr. Jones used the method of difference in this case. Upon investigating, cases where people were sick and people were not sick, she found out that those who were sick had eaten the spinach, those who were not sick did not have the spinach. She concluded the spinach was probably the cause. And that'd be difference because of the difference. That's a way to sort them out. If the effect is present in every case, agreement. Present, absent, difference. Before pressing on, anything about that needs more stuff? So far we've looked at sorting out causation on the individual level. Like, why does my phone not phone? Or why do I feel tired and lethargic? Or why did I do so great on that test even though I didn't study? You know, those sorts of things. Now we turn to general causal claims. Now, a general causal claim is not about, trying to explain like why your phone doesn't work, or why you feel tired, or why you feel great. It's dealing with causation in the population. So again, the question is not, what effect does salt have on me, or what effect would eating eggs every day have on me? The question is a general causal claim. What effect does salt have on diet? Not my diet, not your diet, but in general. Because the government's not like concerned with us, individually. They don't do like, what effect does salt have on TED? It's what effect does salt have in general. So when we're dealing with general causal claims, like does smoking cause cancer, does salt cause hypertension, does eating lots of dairy, is that good for you? These are all questions about the whole population as a whole. So the way we deal with this is the following way. We make general causal claims. And the causal claim, when you think of causation, we generally think of like pretty dramatic causation. One thing definitely causing another. Typically think of like 100%, probability, like an extreme example, like rockets blowing stuff up, that kind of causation. But, and this is what can cause a lot of trouble, causation in a population can be a really weak, very mild, very non-blowing up thing. It can look so mild that, as I'll see when I give some examples, people can exploit this to say, oh, there's really no cause at all. So when we say that one thing causes another in a population, we're not claiming, well, let's use a concrete example. Suppose we say smoking causes cancer. Now, one way to look at that is, if you smoke, you get cancer. Everyone smokes, get cancer. But we know that's not true. Plenty of people who smoke don't get cancer. There are plenty of people with cancer who've never smoked. What we mean when we say smoking causes cancer in the population is this. There'd be more cases of cancer in the population if everybody smoked than if nobody did. And that's a really sort of mild, kind of weak, connection. And again, it can be so mild and weak that we may think, well, is that even causation? And the answer is, yeah, it is. Because if it makes a difference, then it does make a difference. Now this sort of weakness, sort of really sort of mild, account of causation, does provide a sort of conceptual, gap that can be exploited. So think about, the smoking example is a good one. Tobacco companies knew pretty much from the get-go that smoking was super dangerous. In fact, intuitively, people should have known that because when there's a fire, they don't say, hey, everything, stay away from the fire, but that smoke's fine, just keep breathing that smoke in. They always tell you to get down on the floor and avoid the smoke. And so you might think, well, if burning house is bad for you, then inhaling smoke would be bad for you too. Now, when people started to claim that smoking maybe caused cancer or is connected, the tobacco companies would say, well, so many people smoke and very few get cancer, how is there any real connection? It's not like if you, smoke, you're going to automatically get cancer. It's not like the connection between like drinking poison, drinking a gallon of chlorine, you're going to die. And so this is like, well, is it really a cause? Is there really anything going on there? And for years they were to exploit that because what you can do in the case of, well, like arsenic, if you drink some arsenic, you just die. It's like, if everybody drinks arsenic, they die. If you drink arsenic, you die. Clear connection. But in the case of something in populations, the connection is so small, they can say, well, is there really a connection? And so what you have to do is you just can't show, like explosion connection. You have to show statistics that here's like cancer rates among people who don't smoke over time, the population, and here's the cancer rate of people who, as they smoke, years of smoking, and you have to establish this causal connection. It's usually not a huge difference. It's not like people who smoke are like 1,000 or 1,000,000 times more likely. It can be a relatively small difference. And it's hard to, one, show a small difference. It's also can be hard to convince people, okay, 6% more people have cancer because of this. People say, well, is it really a connection? The answer is, oh, yeah, it's a small one, but there. And so tobacco companies could say for years, oh, is there really a connection? I mean, they knew there was. Their own science said so, but they could have this sort of deniability that is there really a connection? Now, a similar thing is being done with climate change. If you believe the scientists that it's really happening, whenever we have a storm or something, people can say, but is it really climate change causing it? Because it's not like in a sci-fi movie where like the climate changes and then there's like weird purple lightning zapping people and blowing people up, and giant monsters coming out of the Pacific attacking us. It's not that dramatic. It's just a little a little warmer. You get a few more storms. The storm's a little more intense, and people can say, well, is it really climate change? And it's easy to deny because we're talking about not huge, dramatic, monsters coming out of the Pacific Rim here. We're just getting small shifts. And it's easy to say, well, is there really causation there? But when we're talking about causation on a large scale, again, it's a very sort of low bar. Namely, if you exposed everyone or everything to that effect, there'd be more cases than if no one was exposed. Now, it can be hard, as you imagine, to find that effect, because if it is very low but real, you could test lots and lots of people and still get no result. So that's kind of the problem. So how do you sort out causation in the population? Now, if you're dealing with individuals, you can test yourself. So if you wonder, does eating a lot of salt, does that crank up my blood pressure? Hey, not recommended, but eat lots and lots of salt, keep taking your blood pressure. And you'll know, with a pretty good chance of knowing what effect that has. So if you keep consuming lots of salt, more and more salt, your blood pressure keeps going up, probably the cause. But we're talking about the population as a whole, more problematic. So here's how we handle that. So if we have a claim like too much salt increases your blood pressure, or smoking causes cancer, or any other general causal claim in the population, that say economic poverty increases people's chance of being sick, weakened immune system. So here's how you test it. So the problem is, of course, we get typically big populations, and we're trying to look for causal factors that might be very small, might have a very small effect. So how do we find it? Well, here's what we do. In many ways, this is a version of a generalization, because it is. Here's how it works. Now, the gold standard, perhaps even the platinum standard, is what's called in the book the controlled cause-to-effect experiment. So it's got three things going on: controlled, cause-to-effect, experiment. So how do those break down? Well, the control part is this. When you conduct this experiment, you're going to have two groups. One group is called the control group, and one group is called the experimental group. Now, this also ties into why it's an experiment, so kind of killing two birds in one stone. The experimental group gets exposed by the people running the experiment to the suspected cause. So what makes the experimental group experimental is they're exposed to the cause, and what makes it an experiment is that those conducting it do the exposing. For example, suppose the question was, what effect does a particular sports nutritional, like Goo or Stinger or Gatorade or Powerade, have on, say, performance in a marathon? If that was your question. What you do is you'd run this experiment, so you get two groups of people, and one group would be taking the goo, Powerade, Stingers, whatever, and you'd be providing them, and you would be the one saying, here, use this. Now the control group, ideally it would be just like your experimental group, except it doesn't get exposed to the suspected causal factor. Now, to make it work as well as possible, you want your control group and experimental groups to be perfectly identical except for that one factor, which, as you might imagine, can be pretty tough. Now, one way to do this is to run the experiment, once with the same people under the same conditions, running it, with the causal factor, and then running it again with the exact same people in the same conditions without the causal factor to see what the difference is. So, if you were, in sports physiology and you're doing your master's or PhD on the effects of these refueling things, you could run it that way. You get a group of people, you have them do ideally like multiple events using, say like they use goo every 20 minutes during a 10K, and then you have them run 10Ks with no goo, and then you compare their multiple ones under similar conditions, and you compare their performance. And the idea would be as a controlled experiment because ideally they would be the same people, same conditions, etc. The only difference being the goo, for example. So the control part is you have one group non-exposed to the suspected cause, the experimental group exposed, which also says why it's an experiment, because those conducting it, they do or direct the exposing. Now the cause to effect thing is this. That part is when you're conducting the experiment, you know the cause, and your question is, I wonder what this does. So in this case it'd be, I wonder if goo actually has a performance, enhancement. Does it actually help, like in a 10K? And so you know what you're trying to test, but you don't know the effect. So it's controlled because you split the members of the experiment into control group, not exposed to it, the experimental group exposed to it. It's an experiment because those conducting it are exposing the experimental group to the suspected to the cause, and it's cause to effect because you wonder what does this do. Now, there can of course be various complications and problems. For example, one of the base challenges is getting your true groups to be alike, enough. So if you're comparing true groups of runners, you have to be careful to get people with similar performances. So for example, if by chance you ended up with, say, people who are naturally better runners or better trained runners in your control group and experimental group, then the goo might actually help, but if these people in general are better, so the exposure control group was like former college athletes, soon after college who were still training. And your experimental group is like casual runners. You can give them all kinds of goo, they're still gonna do worse. So you'd want to have a mix. Also, it would be factors, like age. People get way slower when they get older. Person's, biological sex, that affects people's athletic performance. Also, amount of rest a person's getting, all kinds of factors. And also the course can matter. Like if you run it on, if you do this on like a hilly course and this on a flat course, so you want to make the groups the same as possible, same conditions. So one challenge is trying to make these as close as possible. Another factor is a psychological factor when you're dealing with people. Namely, if people think they're getting something that does something, there's a placebo effect. They'll think it's doing something. So one thing, like if you're testing, you take sports stuff. Maybe the sports nutritionals, even though they have sugar and stuff in them, maybe part of it is psychological. That, you just think you're gonna do better, and you do so because you think you get something benefiting you, like kind of like a lucky item. And you do better, but it's not the goo. It could be anything. It could be a rabbit's foot or whatever. And so the placebo effect is a thing to take into account, because if people think they're getting something, it'll generally tend to affect them, which is kind of a problem with testing things like performance, painkillers, etc. If people think they're getting a painkiller, they feel less pain. Now you could, of course, still say, well, I guess in a way it does work. If it works psychologically, then it still works. If you run faster eating a goo, maybe it doesn't matter whether it's the caffeine in the goo or just psychological. Like, I got my goo, I'm faster today. Now, to counter that, one thing people will do is, the placebo thing. The people, ideally you'd have the people doing the goo, they would get real goo, and the people who don't get the goo would get something goo-like. That is like no sugar, like it'd be like some type of maybe like a starch, or just like a neutral syrup with like a non-sugar sweetener, so it tastes like goo. You also want to control for the different effects, because maybe taking the time to tear it open and when you eat it, maybe that has some effect too. So you want to make them the same as possible, which is why when they're doing medical tests, people get real pill, people get fake pills. Or in the case where they're doing surgery, and they rarely do this in surgery too, real surgery, fake surgery. And so you'd run it, and then once you get your results, you compare them. What is the difference between these two groups? So if this group ran faster, how much faster? Or if this group, reported less pain, well, it's kind of subjective, but how much less pain? Or if this group with a surgery reported, a certain range of motion, how much more? Now, you pretty much expect every time you run an experiment, these two groups won't be identical. I mean, it could happen by pure chance, but in general you expect some difference. So a question would be, if you see a difference, does that mean there is really a difference? Well, you might say, well, yeah, there's clearly a difference. But the question is the difference significant in terms of the suspected cause? Again, going back to the two groups, if you use the same people, same course, have them, do the goo, run, 10 miles, time them, then you do it again, no goo, 10 miles, time, keep doing it over and over again. Even the same people running the same course, you're not going to get the exact same times. People aren't like machines. We don't exactly run exact speed constantly mile after mile after mile. So you'd expect there to be some difference, no matter what. So how do you tell when the difference makes a difference? And when can you say there's really no difference? Now, going back to the tobacco example, the tobacco companies would often try to say, well, yeah, there's a difference, but of course there's going to be a difference. No two groups are going to be the same, and so that's not really significant. So how do you tell when it is? Well, there is, of course, a chart for that, because everybody loves charts. Now, it's similar to the generalization because it is. Because what you're doing then is this. You run your experiment, get your results. Then what you do is you extend it to the whole population. So the part where you apply to the population is the generalization. So you pull out your group, you split it into experimental and control, you run it, and then you're extending your results back to the whole population. So you're generalizing. Now, just like with generalization, the bigger this group is, the more accurate the results will be. So if you have a very small group, your results could very likely due just to chance. Like if you had one runner and one runner, you're going to expect very different results. And the more people you get in the group, then the more accurate the results will be. And ideally, the perfect experiment would be literally everyone. You take everybody on Earth, okay, you 4 billion line up here, get your goo. You 4 billion line up there, no goo. Okay, run 10 miles. Okay, come back and let's see how it goes. In that case, you'd have a pretty good result. But of course, just like with generalization, getting more and more people, test subjects involved, the cost and time goes way, way up. So how do you tell when the results actually are statistically meaningful? Well, the chart. if you have 20 people or 20 entities in your experiment, 10 in each group, that's pretty small. In order to be statistically meaningful, to say there's really a cause, you would need at least a 40% difference. So if someone is running this experiment, say someone's getting their, doing their dissertation, and they're only able to get 20 people, 10 here and 10 here, they would need to find a 40% difference to be able to say with confidence there really is a difference. And the odds are they're not going to get it. Because if goo did a 40% improvement to your performance, that stuff would be probably illegal. Probably would have some really sketchy chemicals in it. But it doesn't boost it, nothing boosted that much. Cheating like with a motorcycle or something. Yeah, so in that case, the results would be effectively useless. As your group gets bigger, you can capture smaller and smaller differences because the population of your group is larger and the factors that are due entirely to chance start to get taken out. And again, if you had the whole population in your experiment, then the results would be super accurate. Now, so what's the takeaway on this? Well, one is, if you're ever conducting an experiment, say you go to grad school and you're doing a thesis or dissertation, and this is something you learn along the way, of course, you need pretty good sized groups, because otherwise, unless what you're dealing with has pretty dramatic effects, you're not going to notice it. So, suppose you're working with a sports supplement, and it's amazing. It gives like a 3% boost to performance. Well, you're not going to catch that until you get to a really big group of people, because it's just going to be washed out in the differences between individuals. And so if you have a small experiment, unless the difference is really big, it's not going to show up. Now, another takeaway is this. One thing that's been exposed in recent years is the science journalism. In many cases, it's not people. There's often journalists who know nothing about science, and they're just cranking out things, to put on the web for basically clickbait. So one factor is you have people who don't really know science, not scientists, and of course there's high pressure to get people to, go to the website, and look. So titles have to be sort of dramatic and eye-catching. Things like, chocolate causes loss in weight loss, or red wine is good for you, or chocolate is good for you. And those are all things people want to click on because people, they probably want to drink wine. And what stops most people is it may be bad for them. But if you know that drinking wine is great for you, why not? Or like if you find out donuts are amazing for you, they cause you to lose weight. Great. Now because of that, you often get bad science ends up on the web. And so you do end up with things like, chocolate causes weight loss. Doesn't. Red wine, is good for you. Probably not really. But how do they get those results? Well, the way they can get them, of course, and there was a person who went through, he got some heat for it, but he claimed that his point was to show how it was super easy to run experiments and get the results that, kind of legitimately not actually, kind of illegitimately legitimate, using, legitimate methods kind of in a tricky way, where you could get the results that seem dramatic. And one thing he pointed out quite correctly is this point, that you can get results if you use really small groups. So for example, suppose you get 20 people, you give these people like chocolate, these don't get chocolate. If you run enough groups, you're going to get a group where the people eating chocolate lose weight relative to the non-chocolate eaters. So you can say a study shows that eating chocolate caused a loss, like you could say like a 6% loss in weight. And that would be perfectly in a way true that that's the result. This group had a 6% loss over this group. But if you know the size of the experiment, you'd know that that is meaningless. And many of these sort of like shocking results are shocking because they're not true. They're really small groups and effectively meaningless. And it's amazing because how much there is. And once you know this chart, it's actually pretty useful because you go and you'll see those shocking results like, eating this had this result. Then you look at the size of the experiment, it's like 30 people. It's like, well, that's meaningless. And so unless you get like a big number corresponding, to the population size, the results are, they mean nothing. They tell you nothing about whether chocolate makes you lose weight, tell you nothing about whether wine's good for you. And it's kind of, also I'm not shocked by it anymore, but I used to be shocked at how many things were reported by the press, mainstream press, not just like sketchy operations, in which the science is just terrible. There's really small, numbers of people in the experimental group, control group, and the numbers don't, I'm sure they're not lying, maybe, but they just have no significance. So a lot of that stuff is just meaningless. But again, people in the sciences, they have to do it to get funding, and the way you get funding is you get dramatic results, which means you often have to do morally questionable things. Because there's not as much public funding of science anymore. So yeah, so as a practical matter, watch out for those tricky things. And again, the reason why it's important is because if you're making decisions about what you eat, or health decisions, then that matters. So if you're deciding, suppose you're having problems with your knees, and you wonder, I've heard about this glucosamine stuff, will that help me? And you come across some, article that says glucosamine, is great, and they refer to some study of 100 people, where the people in the experimental group had a 10% difference in their, their pain. Well, still, that's meaningless. It probably did nothing. And so if you're looking at things for health and diet and so on, that's a good thing to know, because that way you can see this is, it may not be false, but there's really no evidence for that. And the more shocking it is, the less likely it's going to be true. And it's all through, so-called science journalism today, no longer shocking to me, but to a shocking degree. So that's the gold standard, being able to do this. Now another part of it is repeatability. You should be able to, one thing you probably learned in the science classes, if you're able to get the results from an experiment, you should be able to do it over and over again. Now, you expect some difference. So if there's like a different result, they're not identical, well, yeah. But they should be still statistically significant. So if someone does an experiment once, and they get a result and say, look, it had this effect, and then it's run again, and it's different, and it's run again, and it's different, and they can never be replicated, then you suspect there's something going on. Now, it could be, of course, that the original experiment was accurate, and the ones that are being conducted are just getting it, because it's inductive, they could be getting it wrong. But if it can't be replicated, then you suspect that there's something, something wrong about it. It doesn't mean the people doing it were dishonest. Their results could be perfectly legitimate. It's just that when it's done, like because every time you do the experiment again, in a way you're increasing the population size. And so it may turn out that that was kind of an odd result, and then more experiments will show it. And I would say it's shocking about how much science is not tested, but it's not shocking anymore, because one thing that's been, again, another sort of controversy that came out, especially in psychology, is that they had all these experiments, often with shocking results, and it turned out no one could replicate them. They go and do them again, it's like, no, that's not happening. Now, the reason why that kind of gets by is because, again, to get funding, you need to get attention, you need to get interesting results. Ones that are like obvious, don't. Also, of course, a lot of places are getting funding from industry. So I know people, for example, they're funded by a company making supplements. And if the company is funding your research and providing all your stuff, it's kind of hard to say to them, yeah, the results say your stuff it does nothing, or it makes people worse, because they're not going to say, thank you for telling us that our product is crap, here's some more money, prove us to be more wrong. Now, this is not to say that scientists are automatically being corrupted, but that is a temptation. If you get published or perish, you've got to keep your funding up, mostly from the outside industry. And so when you're looking at today's science, it's not that science is bad, it's that you have to look at what are the factors that affect the results. And it would be, size, it would be the pressure to have, cool, exciting titles, and also, of course, the need for funding. So you should be suspicious of any results which are, going back to chapter 1, things that are potentially biased. So if it's sponsored by, oh, you know, if a experiment shows that you need to hydrate, you know, lots with Gatorade, sponsored by Gatorade, doesn't mean it's wrong. It just means you should be suspicious, because maybe the results are skewed. Also, one reason why they don't go back and test them, because there's no real fame in like running an experiment that's already been run. You know, trying to in getting negative results, saying this doesn't work. That doesn't go on the headlines. The headlines is not, guess what? Drinking wine is not great for you. That's not a headline. You know, that's not a click, because everybody says, yeah. Or eating lots of candy, not good for you. Well, that's true, but not very exciting. Okay, so those are all things to be on guard against. So that's control of cause to effect experiment. The key things to recognize here would be what it is. Namely, you have a population and you wonder, what does this cause do? So you pull out a group, split it into the control group, which doesn't get exposed to the cause, the experimental group, which is exposed to the cause. Ideally, they should be as same as possible. You introduce the cause, wait for the results, and then see if they're statistically significant or not. If they are, then you can say that that cause probably produced the effect. Now I say probably because this is inductive reasoning, and if you do everything correctly, you could still turn out to be wrong. Which is why it's important if it turns out later that an experiment is overturned, the original experimenters could have been doing everything perfectly legit, everything done correctly, but it's inductive reasoning. Things can always go wrong. That's, you know, that's sciencey stuff. The way to spot one of these, like in a true-false question or multiple choice question, is look for those key factors. You've got the cause is known, the effect isn't. You've got those conducting it, introducing the cause. Now what about cases where, for some reason, you can't introduce the cause, or it'd be wrong to introduce the cause? For example, if we're ethical, and we wonder what like uranium does to people, we're not going to expose people, we're not going to say to people, hey, come do our experiment, here, have some uranium, because that would be wrong. Now, people have done terrible things to, if you look at the history of the United States, people have done horrible, terrifying experiments on people, even in the 20th century. Probably going on right now, terrible stuff. But if we're being ethical, and we're dealing with stuff that's dangerous, we wouldn't want to expose people to it, even if they kind of agreed to it, because it'd still be pretty terrible. So how do we figure out stuff where either we can, for whatever reason, expose people or things to it, or cases where it would be wrong to do so? The stuff is like probably, you know, super dangerous. Well, in that case, we'd use what are called non-experimental cause-to-effect studies. So what's going on here? Well, it's non-experimental, and it's a study. So what does that mean? Well, kind of weirdly, this may seem kind of counterintuitive, we still do have the experimental group, or what we call the experimental group, even though it's not an experiment, and we still, of course, have the control group. Although we probably shouldn't call it an experimental group, technically speaking, because we're not doing an experiment, but that's what we call it. So how does this work? Well, it works in the following way. Here's your general population, and your question is, I wonder what this does. Now again, since it's something where we cannot, or it'd be wrong to run a controlled cost-effective experiment, it's often something bad and dangerous that it'd be wrong to like expose people to, like uranium or poison or disease. And so we wonder, what does uranium do, long-term impact? Or what does poverty do to people? It'd be wrong to make people poor, because poor, you know, that's wrong. And so, but we want to know what it does. So, what do? Well, what we do is this. We take our population, we already know our cause. So our question is, what does that do? So we pull out, let's use an example of, you know, people. Suppose we want to know what, say, exposure to radiation does to people. So we could go to Japan, because they had the reactor there. broke open. And we could get people from Japan who are, the same as the other people near the reactor, but weren't exposed to that radiation. And we can, in our experimental group, we have people exposed to radiation. In our control group, people who are not. Now, it's not an experiment because we don't say, hey, come over here and hold this uranium for a while and let's see what it does to you. They've already been pre-exposed. And then what we do is we run our study and we see what happens. And so, suppose we're wondering, what does this do to health? So we track all the health consequences. And we may find out that, 10, 20 years down the road, this group has more cancer or more some other health issue. And that's how we conduct it. So basically the scenario is, we know the cause, we wonder what did this do, what is this going to do? But we don't conduct it as an experiment. So what we have to do, which makes it less accurate than a controlled cost-effective experiment, we can't take two groups, match them, and then expose one group. We have to try to go in the population and find people who are as similar as possible, except for that one factor. So people who are in Japan, etc., similar ages, except fitness, etc., and then find people who are exposed, match with people who weren't. Now, as you might imagine, this can become problematic because in some cases, people will self-select. Think about like dangerous behavior, like smoking a lot, drinking, etc. There may be things that lead people to drink that could affect the results. So there may be things that, people end up being in this scenario from, say, dangerous behavior that make them different from the control group. That could become a factor. Also, even if there's not a self-selection factor, there could be differences that we just can't account for. For example, maybe that part of Japan, maybe there was like a contaminant in the soil or some chemical in the soil naturally, and these people would have gotten higher levels of cancer anyways. Whereas people who didn't live there weren't exposed to it. Because there are some areas that do have more, say, environmental, natural environmental contamination. So next time, more causal stuff. So have a good rest of the day, and I'll see you on Thursday.